I'm Atsushi Ofori. I present this work. So we believe that the dynamic typing should be included in any statically typed language for various practical needs like communicating with external environments such as databases and persistent stores, writing type-dependent program, manipulating programming resources. Despite such obvious need, dynamic typing in ML, so far realized, is rather restricted. So the goal is to extend ML with dynamic typing orthogonally to all the ML features, which I will explain later. Before that, let me review dynamic typing, which consists of primitive type Dyn, whose semantics is intuitively a pair of value of type tau and a representation of tau, and two language construct of this and this, which is familiar, should be familiar, and associated evaluation rule. So this is so simple and so obvious and innocent looking. And indeed, if the two typing rules as they are shown can be added in ML, then we are done. Meaning that we achieved ML with orthogonal dynamic typing. So to see this, let's suppose they are at this moment magically given. Then, for example, polymorphism and type inference, this is no problem because typing from the typing rule, it is obvious that the ML infers the following polymorphic type. And therefore, any polymorphic code involving these dynamic construct has expected polymorphic typing. Pattern matching is also no problem, because ML pattern matching is orthogonal to its type system. So you can write this kind of code, function f taking Dyn and do coercion to some polymorphic type constructor and do case analysis of this constructor. For example, if T is a list, then you get the ordinary list pattern matching. Furthermore, this mixture can indeed realize dynamic case or type case construct. So I use dynamic case E of some pattern arrow expression. This is a simple syntactic sugar. So user-defined data types are also no problem. You can define arbitrary number of user-defined data type and use any number of any combination of constructor of different type in a single case, dynamic case statement. So now we understand that these two construct most of the feature of dynamic typing are automatically obtained. So now crucial point is the availability of the two constructor for any tau, including type variable, which involves some difficulties. And due to this difficulty, this simple and therefore superior approach has not been taken before. Of course, before this work of ours. So in this work, we have done this simple integration by developing several components. So first component is reification of ground types and values. So these evaluation rules violate phase distinction in the sense that this tau is a static value and this type tag is a dynamic value. So you can't simply mix in evaluation rule. So for this, we do the following. For ground static monotype tau, we generate code that create a type tag at runtime. Furthermore, for the user program to analyze this dynamic value, which is often needed in various practical programming, we also reify runtime value v and a type tag L of tau to user level data types, reified term we call and reified ty. To do this, we include in this type tag all the runtime information such as object layout and develop type-safe conversion functions between values and reified term. We should note that this mechanism only works for ground monotypes without type variables. The second component is type variables appearing in a polymorphic expression. So type tau in this dynamic expression may be a type variable, of course, for a polymorphic expression like this one. So naive evaluation containing this free type variable doesn't make much sense. So this problem is solved by performing type tag passing based on the type-directed record compilation I developed many times ago. As a historical note, this one is perhaps the first proposal among similar approaches such as type class dictionary passing, tag-free GC, compiling polymorphic equality. Since this is the core of our integration of two constructs, I explained the development, which consists of three components. First is type reconstruction with kind annotation of type variables. For those type variables involving in these dynamic primitives, the type inference annotate special kind R for reify. This is the first one. The second is insert type tag abstraction for R-kinded type abstraction. So if you have a type R-kinded abstracted term, then a compiler insert this special lambda abstraction where I reuse T for lambda variable with type, special type ty_rep of T. Now ty_rep of tau is a singleton type that contains one value, that is a type tag of tau. Now third component is insert type tag application at polymorphic instantiation for R-kinded abstraction. Now in this case, you instantiate int so that this type becomes ty_rep int, which is this singleton. So denote this value. So compiler insert this type tag application, right? There is one more step needed to make a proposal more practical. Consider this function, which takes dynamic value and do case analysis, and if this dynamic value is a pair of this function and this value, alpha, then apply this function to value. Any application of this results in runtime type error because alpha, this one, is a vacuous type variable and is therefore eliminated during compilation. In order to do the intended job, we need a locally bound existential types by introducing existential variable, existential type variable in this phrase, in this scope. So we extend the type-directed compilation framework to existential types by performing local type tag generation and passing. We now quickly go through the development. The first is the source calculus definition. This is ML defined with kinding of type variables. I already explained all those types involving in dynamic primitive must be R-kind. This enforces type variable appearing in dynamic primitives to have a R-kind. Second stage is the definition of the target calculus. We need to define type tags, and type tag L contain variable. This is a variable in this language, and type tag has a type with singleton type, right? So using type tag typing, now we define term typing, and for example, dynamic has this kind of a typing rule that L has this singleton type ty_rep of tau of this type tag, right? For the target calculus, we define operational semantics, which represent type tag passing evaluation. And for this operational semantics, we can show type soundness. This theorem that target calculus typing is sound with respect to the operational semantics. Now with this preparation, now we can define type-directed compilation, which is a translation of source calculus typing derivation into the target calculus typing derivation, which is written in this way. And this is actually following the record compilation framework adapted to type tag. As in the record compilation, we can also show the type soundness of compilation, exhibited by this theorem, right? That the compilation relation preserve typing. Combining with this theorem and the previous theorem of type soundness of the target calculus, we obtain that the typing rule of the source calculus is sound with respect to the operational semantics realized by compilation, followed by the execution of the compiled code. The development is fully implemented in SML#. Now the syntax and supporting structured dynamic together realize the integration. The syntax has two special constructs called underbar dynamic as, this is a coercion, underbar dynamic case, this is a type dynamic case statement. Now, Dyntype is refined to take a parameter. This parameter is a partial static structure which is guaranteed to be there. So this is a kind of super type of actual type. And now this bound is written in this way, and supporting dynamic structure consists of various useful functions, including injection dynamic function, and pretty printer, and view is a taking a partial dynamic type and return the static part, non-static part. We show some example. First is pretty printing. Dynamic PP is a pretty printer which is polymorphic and first class. Right? So that means you can use this anywhere you want, as far as it's type correct. So for example, you can define your own data type. This is a list actually. And then you make a function to create a list. And inside of a function, you just call this dynamic PP of some arbitrary, whatever argument you want. And in this case, you try to print this decode and invoke this function. Then this every recursive call, this argument are printed as a record. Second example is JSON. So dynamic structure contain two functions from JSON to JSON, and then this is a simple but very useful function. Import JSON takes two arguments. One is JSON string, and other one is the expression of any type, right? And then this function tries to first import JSON to get a dynamic value, and then try to coerce to this type, the type of the expression you supplied, and then take a view of this part. So this is a partial dynamic. So for example, if you do apply this import JSON to this kind of XY speed color, and the sample is XY, then you get the expected result. So this is a heterogeneous JSON string, and you extract the interested part. So this is very handy manipulation of JSON. Third example is metaprogramming. This code, I have no time to explain the detail, but this code is a variation of some kind of function. I'm the apply pair and type safe evaluator. Some preparation. Now you can write the expression and typed expression, so kind of source typed source expression, and then apply evaluator to get the runtime value of that same type. Right? So the point of this is that with dynamic typing, we can write type-safe metaprogramming in plain ML. The only extension is dynamic typing, without using any fancy mechanism like GADT or various forms of type classes, or even without polymorphic recursion. This could be interesting to compare the power of dynamic typing with various other mechanisms. I end this talk by showing this SML #4.0.0. Please download and use it. Thank you very much indeed.